Welcome to the video where we will be talking about moment. I've included the word torque here because that may have been what you are more familiar with calling this concept of force acting over a distance, but in this class we will be calling it moment rather than a torque. So after our activities in class, last time we met, hopefully you have some idea of what a moment is. So a moment about any point on an object is the measure of the tendency of a force, to rotate the body about a point. So it's the tendency, and what we mean here by tendency is that the object doesn't actually have to rotate, it just has to want to. If it didn't have any supports or anything holding it back, it would rotate. Moments occur when a force acts through a distance. So rather than at one point, as we saw in concurrent systems, it's going to be some distance away from the point. So here's sort of half of a schematic of what we did in class last time, where we had the ruler balancing on top of the wood dowel. And I'm just going to represent the location where we had the force as just a red arrow being a force rather than drawing the mass. And so this is kind of the same as that point that I've labeled as O, feeling a force down with the same magnitude and also some moment. And so because that force is acting a distance away from what we're calling the origin, it has this tendency to rotate. And as we saw in class, that moment is equal to the force times the distance, d. And what is this d? So we call this d the moment arm. And the moment arm is the perpendicular distance from the point we're trying to rotate about. So the perpendicular distance from point O to the line of action of the force. So basically, it's the distance from point O to the force, but that distance needs to be perpendicular to the force. So what happens when the moment is not perpendicular to the force? What happens when the force is not perpendicular to the object? So in this case, we have our same setup, but we have a force acting at an angle. And I can break that force into its component, Fx and Fy. And d is still, when I'm applying my formula, I need d to be a perpendicular distance, okay? So I'm going to break f into its components, and they're going to be Fy equals F sine theta and Fx equals F cosine theta. So what is the moment from the y component of the force? So here again, I'm going to have my schematic, and I'm going to only show Fy. And in this case, the moment is F sine theta, which is the y component of the force, times that perpendicular distance, because they are perpendicular. What about the moment from Fx? So again, I'm going to have my schematic, but in this case, when I draw Fx, here it is parallel to my ruler. What happens to the ruler because of this applied force? Here's Fx. This does not cause any rotation. So I'm asking, does this F cause rotation about the origin? So if you push or pull on a spot, on the ruler, it would not cause rotation about 0.0. So I'm going to summarize this by saying there is no moment when the line of action of a force is through the point of rotation. So moment is a vector. Okay, so we've kind of been, it deals with a force, but it is actually a vector. And we've only really looked at the magnitude. But because it's a vector, it has both magnitude and direction. So the magnitude we've already seen, and the magnitude of the moment is equal to the force times the distance. But what about the direction? So the direction is determined using the right-hand rule for moments. So the right-hand rule for moments, what you do is you take your right hand and you point the fingers of the right hand from the origin, or point O, to the force. Okay, so you see here on my schematic, I've added, see here, this is actually my hand I took a picture of. So this is my right hand and it's pointing from O towards the force. Then I'm going to curl my fingers in the direction of the force that it pushes or pulls the object. So here I've taken my fingers and curled them down. Okay, so my right hand pointing this way and pushing down. And my thumb, which is pointing back into the board or the screen, points in the direction of the moment. So if we thought back to our right-hand rule for 3 dimensions, that's my negative direction, right? So for 2-dimensional problems dealing with moments, if the a positive moment is when an object rotates counterclockwise, okay? And a negative moment occurs when the object rotates clockwise. Sorry about the, yeah. Oh, shoot. All right, sorry, let's scooch back here for a minute, and sorry about this watermark in the way. So, positive moment when the object rotates clockwise, and a negative moment when the object rotates, sorry, I totally said that wrong. It's a positive moment when the object rotates counterclockwise, so counterclockwise, and a negative moment when it rotates clockwise. And in 2-dimension, that's all you need to signify direction is positive or negative. So I'm going to do a second video where I do an example of determining moment. But in this video, I'm just going to give the concepts. So we're going to go ahead and move on to the next set of concepts here in dealing with moment. So I'm going to go through one example here without numbers, but again, you can look at my moment example video to see an example where we solve for moments. So here's a bolt, here's a wrench trying to remove a bolt, and so here's some force that you might apply to this wrench in order to unscrew the bolt. So we're going to use the bolt as point O that we're trying to rotate about and try to find the moment about the bolt. And I'm going to call the distance along the bolt from O to F, I'm going to call that R. But right here you can see that we have no perpendicular distance, right? R and F are not perpendicular to each other. So I can't just do that the moment about O is equal to F times R. We need to do a little bit of manipulation. So what I've done here is broken this up into 2 different parts. So first, I can break the force into 2 components. So first I have Fy pointing up, and that acts a perpendicular distance that I'm going to call R sub x away from point O. And then I'm going to have a second part of the moment, and it's going to be that moment caused by the force in the x direction, so the x component of the force, and it acts a perpendicular distance equal to ry. So if I add those together, I'll get the whole moment. So m1 is rx times fy, and I'm going to add to that m2 equals ry times fx to get m total is equal to m1 plus m2, which is rx fy plus ry fx. So this leads us to a very important theorem. And so this brings us to an important theorem called VarigNons Theorem, which states that the moment of a force about a point is equal to the sum of the moments of the force components about that point. So if I have an object in some point O and some force acts on that object, I can determine the total moment about point O. Here's my axes, and here's the force. It has two components, fx and fy, and that fy acts a distance of dx away from the origin, and fx acts a distance of dx away from the origin. So mo is going to be equal to fx dy and fy dx. But let's take a moment and think about what direction that these two moments are going in. So first, we'll look at fx times dy. So if I look at fx, here it is, and how it is pushing that object, it's going to cause the object to rotate down, right? So this, according to our convention that we discussed on the previous slide, is the negative direction. So I need a negative sign there. And then if I look at fy times dx, I can see that this is going to push the object up and around in the counterclockwise direction. So that needs a positive. So that sums up how we talk about vectors in the scalar realm. But we can solve vectors, we can solve moments using vector formation. And so previously when we did m is equal to f times d and using the right-hand rule, we call this the scalar notation for determining moments. We can, however, do a vector formation, and we write that using a cross product. So we say mo is equal to r cross f. And this is the vector notation for moments. So if you need a reminder on what the cross product is, I encourage you to read your textbook, sections 3.4 and 3.5, for review of cross product and some other vector math. Additionally, there might be a review document up on Camino that summarizes some of these vector math concepts. So here again is my ruler balancing on the dowel, and now I have my force and it's acting at an angle. And previously I had called the distance from O to the force distance D, but I'm going to go ahead and erase that and instead call it R. Okay, so we're going to define what these terms exactly are. So MO, with a vector on it, is the moment from F, the moment that F causes about point O. And R is a position vector, so you'll have to remind yourself exactly what a position vector is. And it's the position vector from point O to any point on the line of action of the force. Okay, so again, if you review your vector math, you'll see that MO is R cross F, can be written using this matrix math. So we have IJK across the top, RX, RY, RZ in the middle, and FX, FY, and FZ on the bottom. So it's important to note here that the moment is R cross F, and that order matters. So you need to have R here in the second row, so RX, RY, RZ, and F in the bottom row. If you mix these up, you're going to get the incorrect answer. So following how to solve this kind of vector math formation matrix, you'll get MO is equal to RYFZ minus RZFY. And so you'll see if you look back up at the vector, the matrix here, that this is RY times FZ and then minus RZ times FY, and that's multiplied by I. Again, review these concepts from the book and the handout, and it will become more clear. Then I subtract from that Rx times Fz minus Rz times Fx times J, and then Rx, I add to that Rx times Fy minus Ry times Fx times K. And that's how you solve this matrix form to determine the vector formation of a moment. So we're going to end quickly with an example where we find the vector formation of the moment. So here is our object, and it is 0.4 meters in the y, 0.4 meters in the x, and at the lower end there's a force of 400 newtons that acts 30 degrees below the horizontal, and point O is up in the top left side. So we would like to determine the moment from that 400 Newton force about point O, and we're going to use the vector analysis. So MO is going to be R cross F, and in this case my position vector is 0.4I minus 0.4J. So what that means is to get from O to the force, I need to go over in the positive direction 0.4 meters in the x direction, and then down 0.4 meters in the y direction. And my force is 400 cosine 30 times I minus 400 sine 30 times j newtons. So my moment is going to be the vector notation. So here I'm going to write it out for you. And if you solve that, you will get negative 58.6 Newton meters, K. So if you do out this vector math, you'll see that it's only in the K direction. What happens if I change R? What happens if I change the position vector from O to some point on the line of action of that force? So if I extend this line of action of this force all the way to the left-hand side of my object, you'll see that it acts 0.166 meters below point O. So clearly this is not to scale. But our new R is 0I minus 0.166J meters. And when I solve my moment matrix, it changes a little bit. The only thing that changes is the line for R, and it now becomes 0, negative 0.166, and 0. But my F line remains the same, and if I solve this, I get negative 57.5 Newton meters. So if I compare what happened the first time and the second time, you'll see that I'm off by a little bit, which is probably within the realm of rounding error. So what I've shown here is what is known as the principle of transmissibility of a force. And what this means is that the moment of a force about a point depends on the magnitude, line of action, and direction of a force, and not on the actual position of the force on the line of action. So I can say that the moment about point O is equal to R1 cross F, which is equal to R2 cross F, which is equal to R3 cross F. So any combination, any way you can get from point O to the line of action of the force, you'll get the same answer. So there you go. There's a quick summary and introduction of moments. Hopefully it reiterates some of the points from the activity we did in class, and you have a better understanding about moments. In class next time, we're going to do a bunch of practice problems practicing how to determine moments. So see you then. Bye.